Welcome to the last set of lectures for this course. So today we're going to be starting by looking at eigenvalues and eigenvectors, which might sound weird, but they turn out to be super useful. And in the second part, we will actually see how these help us solve a number of different problems in the sciences. So last week in the tutorial, we had a look at a model where we had a bison population that was divided into 3 different age classes. And we had what was called a Leslie matrix that helped us figure out how the population would change from year to year based on the likelihood that, for example, a calf would become a yearling would become a female adult, and a female adult would have a calf. And the Leslie matrix we had a look at was one that's shown here. And we said that we can calculate the population at time t plus 1 if we know the Leslie matrix and the population at time t. And we just multiply the population by the Leslie matrix. And what we noticed, hopefully, by the end of the tutorial, was that by the time we got to about year 4 or year 5, although the population as a whole was still increasing, the ratio of the different classes was starting to stay the same. So, for example, if you look at year 4, and you look at the fraction of the total population, which was 184, that were calves, it was about 0.24. The fraction that were yearlings was about 0.13, and the remaining 0.16 was the adults. And then if we look at the following year, we saw that the same fractions hold. So it seems like there's a kind of a steady state, which is a steady state of the distribution of the population, so that once the population gets there, each year, each age group increases in the same ratios. So it might be useful to know how this works in a little more detail, what's going on, and that's really what we're going to have a look at. So as we've just said, we've seen that each year, once we're in our stable state, each age group increases by the same proportion. So mathematically, what we can do is write down this equation here. So the population a year later is the original population, whatever that distribution is, just multiplied by some factor lambda. And if we knew what that factor lambda was, then we wouldn't actually need to use L, we could just use lambda, and we'd know by how much our population grew each year. So just in case you haven't seen this before, this is the Greek letter lambda. All right. So let's see if we can find this lambda. Now, we know that at any time, our population at time t plus 1 is given by our population at time t multiplied by our Leslie matrix. And that's true for any t. But since we're particularly interested in finding what's happened when we've reached a steady state, we also have the equation that we've just seen, which says that our population at time t plus 1 is equal to our lambda, our proportionality constant, times our population at times t. So combining those two, because we can get rid of, we can set them equal to each other, essentially what we're doing is we're trying to solve this equation here, which says we want to find the population and the constant lambda, so that if we take our Leslie matrix times that population, it's the same as just multiplying that population by a constant factor. Now it turns out that this is actually a pretty common thing that happens in many different applications of matrices. In general, the thing that we're trying to do is we're trying to find, given a particular matrix A, we want to find some constants lambda and some vectors x, so that if we say our matrix times one of these vectors that we found is going to be the same as that vector just times by some scalar, so just a scaled version. And when we're solving this particular problem, there are names that we call the vectors and the constants. So these x's are called eigenvectors, and the lambdas that we find, the constants that we find, are called eigenvalues. So in many different applications, you will be required to find the eigenvalues and possibly the eigenvectors of a given matrix, always a square matrix. So let's have a look at how we can do that. It's actually not that complicated, and we've got all the technology that we need. So the first thing that we do is we rewrite our equation. So we're going to take our lambda times our eigenvector over to the left. So we've got a times x minus lambda times x is equal to 0. Now let's just be careful here, thinking about exactly what each of these components is. So our A is a matrix, our x is a vector, our lambda is a scalar, and our x here again is a vector. So if we think about it, if we've got a matrix times a vector, we must end up with another vector, which makes sense. So this whole thing is a vector. And over here, we've got some scalar multiplying our vector, so we've just got a scaled version of the vector. So again, we've got a vector. So on the left-hand side, we've got a vector times a vector, so we need to just be aware that this naught on the right-hand side is actually a 0 vector. Okay. And now there's a bit of a cunning thing that we do. Remember our identity matrix, and remember that our identity matrix times any vector is just going to give us, the vector. Well, we kind of use that in reverse. So what we're going to do is we're going to say a times x minus I lambda times x is equal to 0. So I've really just kind of thrown in, it's a little bit like putting in a convenient 1 when you're trying to do something with arithmetic with ordinary scalars. But now what this means I can do is I can, in fact, if you like, factor out my x's. So what we can write is a minus I lambda times by x is equal to 0. So now what I've got over here is, this is a matrix, which I get from taking the entries of A and subtracting off the identity matrix multiplied through by lambda. So this thing over here will really look something like lambda 0, 0, 0, lambda 0, 0, 0, lambda, depending on whatever the appropriate dimensions are. All right, what can we say about this? Well, here's our equation. We've got our matrix A minus a scaled version of the identity times by our vector x must give us the 0 vector. So the first thing is that we're assuming that there's at least one non-zero vector x that solves our problem. Because if you think back to our bison issue that we were dealing with at the start, we're looking at a population, and we know for a fact that there are populations that are non-zero that solve the situation. So we're kind of assuming that we can find at least one eigenvector that's non-zero. Okay, but what does this tell us? Well, if you think about it, it means that our A minus lambda I can't have an inverse. Because if it did have an inverse, then what we'd have over here, suppose we could multiply through on the left by A minus lambda I inverse, and then we've got A minus lambda I times x is equal to, and then we'd have A minus lambda I inverse times 0. And then this bit over here would just give us the identity matrix, because matrix times its inverse gives us the identity. So we'd have that x is equal to, and then we'd have whatever this inverse is times the 0 vector, but that's just going to give us 0. So we'd have that our x is equal to 0, but our first assumption is that we're looking for a non-zero x. So we conclude that we can't have an inverse, because if we had an inverse, then the only x that would work would be the 0 vector. Okay, but what do we know about matrices that don't have an inverse? Well, we've done some work with determinants, and we know that if something doesn't have an inverse, then the determinant of that matrix is 0. And this turns out to be really useful. So there's a bit of logic going on here. Read through it a couple of times, but the net thing that we want to take out of this is that if we're having a look at this equation over here, we can conclude that the determinant of that matrix A minus lambda I must be equal to 0. All right, so where does this take us? Well, we can just solve that equation and it will give us the eigenvalues of our matrix. So we solve the equation, the determinant of A minus lambda I is equal to 0. So we're solving this for lambda. And that will give us our eigenvalues. You will see this crop up quite a lot if you're doing any kind of work with matrices. This is called the characteristic equation of the matrix. So let's have a look. So here we've got just a straight 2 by 2 matrix, and we would like to find the eigenvalues. So we solve that the determinant of A minus lambda I must be equal to 0. So let's work out A minus lambda I. That's going to be 1, 2, 2, 1 minus lambda 0, 0, lambda. So that's going to give us 1 minus lambda, 2, 2, 1 minus lambda, and we want the determinant of that. So we're going to solve that determinant is equal to 0. Okay, well, our determinant is 1 minus lambda times 1 minus lambda minus 4, which gives us 0. And this will give us 1 minus 2 lambda plus lambda squared minus 4, which is equal to 0. And finally, that gives us lambda squared minus 2 lambda minus 3 is equal to 0. And putting that all together, we can factorize. We've got a lambda minus 3 and a lambda plus 1 is equal to 0. And so finally, we find that we have two eigenvalues for this matrix. We have lambda is equal to 3 or lambda is equal to minus 1. And in general, what you will find is that if you have a 2 by 2 matrix, then the most eigenvalues you can have is 2, 3 by 3, the most you can have is 3, and so on. There's a whole beautiful theory behind that you could study if you went on further in maths, but for the moment, that's what you need to know. Obviously, you might have fewer because you might have repeated eigenvalues. You could imagine a situation where, for example, over here, the quadratic that you came up with was something that was just two terms that were identical, so you'd have the same values. So you could have one eigenvalue repeated twice, or you might have two different ones for a 2 by 2. But we're not going to go into a lot of detail there. Okay, so we have found eigenvalues for our 2 by 2. Let's have a look at eigenvalues for a 3 by 3 case. This is just so that you get a little bit of practice finding your determinants and things. So remember that we're going to work with the matrix A minus lambda I. And this is always just the same process. It's a 3 minus lambda minus 1, 4, 0, minus 2, 3, 0, whoops, that should be a minus lambda there, 0 and a 1 minus lambda. All right, and you might be looking at this and thinking, no, I don't want to have to deal with this, but notice that I've picked this particular matrix carefully so that it's not going to be too horrific. So our determinant of A minus lambda I is, well, you write down the first term, 3 minus lambda, and then you look at the determinant of the 2 by 2 that does not have the same column or row. And this will give us minus 2 minus lambda, 1 minus lambda, plus 0. Oh, that was easy. Okay. And the joyful thing that you'll notice is next we should have -1 times the determinant of 0, 0, 3, 1 minus lambda, but that's 0 because we've got those zeros. And if you look at the next term, that should be +4, so that should actually be a plus. You'll find that the determinant of the 2 by 2 that we're interested there, which is this one over here, is again 0. So in fact, our determinant for this 3 by 3 is straightforward. It's just 3 minus lambda, minus 2 minus lambda, 1 minus lambda. So it is conveniently already factorized, and we can just write out straight away that we have, let's have lambda 1 is equal to 1, lambda 2 is equal to 3, and lambda 3 is equal to -2. So we have 3 eigenvalues for this 3 by 3 matrix. Okay, that's nice. Let's have a look at finding the eigenvectors. So we're going to finish finding eigenvectors and then come back to our example and see how these are useful in real life. All right, so once we've found the eigenvalues for a matrix, then, so this should be for each lambda. So you'll find a bunch of eigenvalues, and then you can construct this matrix for each eigenvalue and then solve for x. We've been doing this a lot because essentially you're just solving something of the form bx is equal to 0, and we know how to do that. So we do need to do it using Gauss reduction. We can't find the inverse because we've just said that b doesn't have an inverse, but that's okay. We know how to do that. Okay, so let's find our eigenvectors for the following matrix. So the eigenvectors are linked to a specific eigenvalue. So let's start by looking at our first eigenvalue, which was, let's call this one 1 and that one 2. So let's call, so we've got a 3 and a -1. Okay, so what we're looking at is we want to solve the equation which says, so this is 1 minus 3, so that's -2, 2, 2, and -2, times x1, x2 must be equal to 0, 0. So lambda 1 is equal to 3, let's just make this clear. A minus lambda I is -2, 2, 2, -2. Okay, well, we can do this using Gauss reduction, and we can actually keep it very simple. So we've got a -2, 2, 2, -2, and 0, 0. And pick your favorite method. I'm just going to take -1/2 times row 1 so that I get my 1 up in the top left. Notice the great thing here, you're not going to have to worry about this column because zeros added or multiplied are always zeros, so you have a bit less computation to do. And I think I'm going to do the same thing here as well, so I'm going to divide through by 2. And you'll notice, and this is something that you will find in every time you're finding eigenvalues, you will have a row of zeros, because notice here, if I now take row 2 minus row 1, my row 1 is going to stay the same, and I've got a row of zeros. And that's all I can do. So how do I write out this solution? So we've talked a little bit about rows of zeros, and I didn't make a big deal about it, but now we're going to learn how to write them out properly. So if you have a row of zeros in a situation like this, it means that the variable that belongs to that row, so remember this would usually tell us about x2. If you've got a row of all zeros, that tells us that x2 is what's called a free variable. It can take on any value. So this says x2 is a free variable. It takes any value. So in order to demonstrate in order to show that in our solution, we write x2 is equal to t for t is any real number. Okay, how does this help us? Well, now we can rewrite the equation that we get from here. This would say that x1 minus x2 is equal to 0, and we would rewrite this as x1 is equal to x2, but we know that x2 is equal to t, so we end up with x1 is equal to t. And so finally, our solution becomes x1 is equal to t, x2 is equal to t, and if we want to write that as a vector, then we write that as our vector x is equal to 1, 1 multiplied by t. And that is our eigenvector. So the first thing that you should notice is that I'm saying that is our eigenvector, but actually this is infinitely many eigenvectors. It is all the scaled versions of the vector 1, 1, scaled by some factor t. And this is kind of what you would expect. If you go back to our original equation over here, if you have some vector that solves this equation over here, if you just multiply that vector by some scalar, so by 2, so you multiply both sides by 2, you will again have a solution, because the 2 times 0 is just going to give a 0. So it shouldn't really come as a surprise that our eigenvector for a particular eigenvalue is actually a whole set of eigenvectors. All right, let's find the next one. So let's add a page here. So now we want to find the eigenvector for our second eigenvalue, which I think was -1. Yes. So maybe take a moment while I'm trying to sort this out here and see if you can work out what the eigenvectors are for lambda 2, which is -1, and then come back and we'll sort it out. Okay, well, I hope you gave it a try. So now what we're doing is we're solving this equation. So it's going to be 1 plus 1, so that's 2, 2, 2, and 2 times x1, x2 is equal to 0, 0. And even more straightforward, we've got, we're just Gauss reducing this thing. And you can see straight off that our solution must be this. So again, we have that our x2 is a free variable. So we say let x2 be t for t is any real number. And then we can write out our first equation over here, which would be x1 plus x2 is equal to 0, would give us x1 is equal to minus x2, but we're letting x2 be t, so we've got x1 is equal to minus t, and x2 is equal to t. Putting this together in vector form, we have that our vector x is equal to, well, it's going to be a -1 and a 1 times t. So it's fine if you leave things in this form here, or you can put it in vector form like that. So again, you see we've got a whole family of eigenvectors for the eigenvalue -1. Okay. So I'm going to leave you to find the eigenvectors of this matrix. It's really not that bad, and I will put them in the final solution. Just give it a go, just because it's good practice, but it's actually because we have, this is called an upper triangular matrix, so it has zeros below the diagonal, which makes everything a lot more straightforward. you should find that the Gauss reduction is pretty straightforward. Okay, so now we know how to find eigenvalues. So those tell us the scalar, which you can multiply a vector by, that will give you the same effect as multiplying that vector by the original matrix that we were thinking about. Okay, and we've also found all the vectors for which this is true. So it's not true for any vectors, but there are many vectors for which it is true, and we know how to find those. Those are our eigenvectors. So if we go back to our bison example, you could go ahead and solve this, but I just asked Wolfram Alpha to do this. And you will find that the eigenvalues for this Leslie matrix are 1.105 and then two complex values. And that shouldn't come as a huge surprise. When you're finding solving the characteristic equation for a matrix, you're solving a polynomial. We know that some polynomials have complex roots, so no big deal. But the key thing here is that if we think about the situation we're looking at, the eigenvalue that we're interested in must be the real one, because we don't have imaginary cows, or at least, don't have imaginary cows if you're a farmer. That's not a good idea. So it must be that this is the eigenvalue that we're interested in. And again, if you got more into this, you would learn about what the complex eigenvalues tell you. They do have information, but for our purposes, we just care about the real ones. Okay, so our eigenvalue that we care about is 1.105. What does it mean? Well, if we have a look at our data that we had, if we look at our growth rate, which we've just found, so that's our lambda, 1.105, what it tells us is that if we know how many cows we have, or what our population is at year 4, then simply by multiplying by 1.105, you will get the number of calves, yearlings, and adults the following year. So that's quite powerful. Previously, we had to take the population from year t and then multiply it by the Leslie matrix to find the population the following year. But once you know the eigenvalue, you just straight multiply by the eigenvalue and you're good to go. So that's kind of useful. And it also tells you very clearly overall how your population is going to grow each year. So you might not be particularly interested. You know that you've got a stable population. You don't care about the calves, yearlings, and adult division. All you want to know is how many bison I'm going to have. Well, 1.84 times 1.105 will give you 203. So that's nice. But we can actually go a little bit further. So if you find the eigenvectors corresponding to our growth rate eigenvalue, you would find that they look like this. So again, we've got our free variable, which we would expect. And then we've got some factor multiplying whatever our population in our x3 group is. How does this help us? Well, in fact, it means that so long as we know one value, for example, if we know that there are 128 adults, we know if we're in our stable population how many yearlings and calves we have, because if we take, for example, this one, we will have 0.206 times 128. And if you check that, it's going to give you 26. And if you have a look over here, 0.380, which is this equation over here, times the number of adults that we have, will give you 49. So there's a lot of information included in our eigenvalues and our eigenvectors. So our eigenvalue is telling us our growth rate, but the eigenvector over here essentially encapsulates the ratios of our stable population distribution. So you could use this for all kinds of calculations. For example, if you know that you want to have a total of 1,000 bison and you want it to be in a stable population, then you could plug together and you would know, well, x1 plus x2 plus x3 needs to be equal to 1,000, but you know that x1 is equal to 0.380t, so this would be 0.380t plus 0.206t plus t must equal 1,000. And you could solve for your t, and that would tell you how you should buy calves, yearlings, and adults to go straight to having a total herd of 1,000 in a stable population distribution. I mean, obviously the following year it would have grown by a factor of 1.105, so it's not going to stay at that, but the distribution of ages will stay the same. So one more thing to notice about this is our eigenvalues and our eigenvectors depend only on the matrix. So although we, in our example, started by looking at a particular population, that initial population didn't have anything to do with where we ended up. The growth rate and the eigenvectors determine exactly what your final population distribution will be. So it might have taken a little bit longer if we'd only started out, for example, with, 50 adults. It would have taken longer, but we would have eventually got to the same population distribution. Okay, so key things to know. Please make sure that you can find eigenvalues of 2 by 2 and 3 by 3 matrices. If I give you a 3 by 3, I'll make sure that it's a nice one that has lots of zeros, so it's not going to be too hectic. And then once you know how to find eigenvalues, make sure that you can find eigenvectors as well. All right, so one more lecture after this, just to look at a few more applications of eigenvalues and eigenvectors, and then we're done for the term.